Swayam Prabha. Digital India. Educated India.
Hello and welcome to this first lecture of the course Advanced Dynamics. My name is Anirban Dasgupta. I am from the Department of Mechanical Engineering at IIT Kharagpur. To begin with, let us see what dynamics is all about, which you of course know. Dynamics is a study of motion of particles or extended bodies. Now, these bodies can consist of, this study consists of two parts. One is, the first part of dynamics is called kinematics. So, kinematics is the study of motion without any reference to forces. Because there are no forces involved, it is purely geometric study. So, inertia properties, mass of particles or inertia of the bodies do not appear in the study of kinematics. On the other hand, the second part of study under dynamics is kinetics. Kinetics is the study of effect of forces on the motion, and hence it involves the inertia properties of the bodies involved. So, these are the two parts of dynamics. So, dynamics consists of kinematics and kinetics. Now, out of these two, the kinematics is more tricky, while kinetics is a straightforward step, more or less. So, we are going to start with kinematics, study of kinematics, which is the study of motion. To give you an overview of what we are going to do today in this lecture is, we are going to study motion in one dimension. We are going to look at the commonly used coordinate systems, and we are going to look at some problems. Now, motion in one dimension, whenever we say motion in one dimension, the typical picture in our mind is a particle moving on a straight path, but that need not be always the requirement. It could be a curved path, but the acceleration specification must always be tangential to the path. So, this is the basic requirement. So, acceleration must be tangential to the path. In that case, this can be treated as a one dimensional motion, and the displacement or distance travelled should be along the path. So, in that case, we can always treat even on this curve, motion on this curve, to be one dimensional motion. Velocity is always tangent to the path, as you know. The problem here is, given the acceleration along the path, we are required to find out the speed, which is the first integral of the acceleration or the velocity, and we are required to find out what is the displacement of the particle or the distance travelled by the particle. Now, these cases, we are going to look at some cases which you have seen right from schools. First case is the constant acceleration case, the simplest, then the time dependent acceleration case, and the location or the distance dependent acceleration case. Now, when you have constant acceleration, you know that acceleration is defined as dv dt, d velocity dt is acceleration. You can integrate this equation once because acceleration is constant, and what you have is v as a function of time is the velocity at time t equal to 0, t equal to t0, plus acceleration into the flow of time. So, t minus t0. If you call this velocity at t0 as u to shorten the thing notations, then you can integrate once again to determine the displacement or the distance travelled at time t minus distance at time t naught is equal to the initial velocity times t minus t naught plus half acceleration t minus t naught whole square. So, these relations you have seen before, I am sure. In the constant acceleration case, let us proceed further. If we write this dv dt as dv ds and ds dt, dv ds times ds dt, then you can see here that ds dt is again v, therefore, this becomes v dv ds, and therefore, our acceleration can be written as v dv ds. Now, if I write acceleration like this, and because acceleration is a constant, I can integrate this equation. I can integrate from here to here, I integrate and obtain v square s minus v square s naught, which is the initial velocity at location s naught, is equal to 2 a s minus s naught. This is a straightforward integration, and you have seen this integration before. Now, velocity what we obtain from here, the velocity that we obtain from here, I can find out that expression by bringing this on the right hand side, which I have done here, and taking the under root, and velocity is equal to ds dt, the time rate of change of the displacement or distance travelled. This is the displacement along the path. So, that is equal to plus or minus this under root quantity. Now, this you can integrate once again, and you know the result actually. This result should lead us to the distance travelled result that we just now discussed. So, here it looks in a different form, it looks in terms of the time that has elapsed. So, t minus t naught, and you can see that there is a plus minus sitting, therefore, you can go back in time or forward in time depending on the sign you take, and the sign depends on the velocity at that point. If the velocity were positive, then you have to take the positive sign. If the velocity were negative, take the negative sign, and that way you choose the sign, because sometimes a particle can reverse motion. Okay. Next, we look at the time dependent case. dv dt is equal to acceleration, which is a function of time now. Then you have to write it as an integral. Now, depending on the expression of acceleration as a function of time, you will get you will have this integral. So, the integral depends on the expression of acceleration as a function of time. So, this is straightforward. You integrate once again, you get the displacement along the path, and the limits I am putting from t naught to an arbitrary time t. Next is the displacement along the path dependent acceleration. So, location dependent acceleration. So, dv dt acceleration is a function of s, the displacement or the location of the particle. Now, here I again use the same expression of acceleration. dv dt I am writing as v dv ds, which I derived a moment ago, and that is equal to acceleration as a function of s. Why I did this? Because acceleration is a function of s, therefore, I need to integrate it over s. And if you do that integral, you get on the left hand side, you will get v square by 2 etc. That 2 I have taken to the right hand side, as you can see. This 2 I have taken to the right hand side. So, this comes from integrating v dv, v square minus v naught is the velocity of the particle when s was equal to s naught. Therefore, v square minus v naught square is equal to 2 integral of acceleration over ds from s naught to s. Okay, then you know that velocity, once I have velocity, again the same steps, I take under root, I bring this v square, on this side take under root. I have not done that, I have not written that explicitly, I am writing here v as a function of s, but you should understand that there is this under root quantity sitting, and so v of at s is equals to ds dt. So that implies I can find out time, integrate time as ds by velocity as a function of s. And if you can perform this integral, then you will get the flow of time. Once again, there was a sign to choose, you have to be careful about. So this is the expression of flow of time. Now this integral, if it can be performed, then you will get the time elapsed. Let us look at an example. This example is about a bungee jumper who uses a cord whose free length is 15 meter and reaches a maximum jump depth of 22 meter. That means this depth is measured from the point of jump, as I have shown you here, it is x max is 22 meter from the point of jump. If the acceleration of the jumper with the cord in tension is assumed to be of the form a is equal to g minus b times y. So this is the acceleration of the jumper when the cord is in tension. First it will be a free fall, then suddenly the cord will come under tension, and then it is a restrained motion. So during the restrained motion the acceleration is specified to be g minus b times y, where g is 10 meters per second square is the acceleration due to gravity, for simplicity we are taking that, and y is the stretch of the cord in meter. Determine the value of b, the b that appears here. So the b, the value of b that appears here, we have to find out for the given data. So data is the jumper jumps with 15 meter free length cord and jumps up to 22 meter, and the acceleration, the form of acceleration under tension when the cord is under tension is given. So you have to find out b, so that this b for this jumper, so that these data are satisfied. Okay. Let us look at the solution. Now there are two acceleration regimes, as you can realize. One is the free fall, when the acceleration is exactly 10 meters per second square, that is the specified acceleration due to gravity, and this happens till x is 15 meter. So less than or equal to 15 meter it is free fall. Beyond 15 meter and up to 22 meter for this jumper, there is the second expression of acceleration, which is 10 minus b times y. Now here what I have done is, so y was the extension of the cord, which I have replaced by this x minus 15. So x is the displacement according to this coordinate system that I have here. So it starts from the point of jump. So beyond 15 meter the stretch starts, so I have written x minus 15. So this is valid only for x greater than 15. Now I start integrating, acceleration is constant, so I can the jumper starts with 0 initial velocity, so u1 is 0, and v1, that is end of the free fall, the velocity will be under root 2 gh, that is all known to you. So this is the velocity at the end of the free fall, so it is under root 30 g, and g is 10, so this is under root 300 meter per second. Now in the phase 2, when the cord gets stretched or starts getting stretched, then you have, so the initial velocity for this phase is the end velocity of the first phase, velocity at the end of the first phase, and beyond this the acceleration is given by this quantity. Now here you see the acceleration is dependent on x, therefore I convert the acceleration as v dv dx, which just now we have discussed, and then I integrate. So, on the left hand side I have d of v square by 2 integrated from v1, which is the initial velocity at the restrained start of the restrained jump. So, v1 was the velocity which is given here. So, v1 is this velocity and the jumper goes up to 0 velocity. We are covering the whole distance up to the maximum depth. Therefore, this restrained jump starts from 15 as written here in this limit and goes up to full x max, which is 22 meter. And if I do this integral, you see on the left hand side the limits are root 300 to 0, on the right the limits are from 15 to 22, which is the restrained jump. And if you do this integral, this is straightforward integration of a polynomial, and if you do that integration, finally you will arrive at this value of b. So, I am not going through the detailed steps, but they are written out here for you, and you get b as 440 by 49, and the units are a little strange. It looks a little strange because you have to realize that this b was a constant in the expression of acceleration and it was multiplied by the stretch. So, stretch is in meter. So, b must be 1 by second square, so that b times y, if you remember. So, g minus b times y. So, b times y must have dimensions of acceleration. So, this has dimensions of 1 by second square. So, this is b. So, we have found out b. The next part of the problem is to determine the time of the total time it takes for the jumper to start from the top and reach the x max, which is the maximum jump depth. Now, the total time is equal to the time of free fall plus the time of the restrained fall. So, time of free fall is very easy to find. I am sure you can find out. It starts from 0 velocity and distance travelled is 15 meter. If you know, if you remember, this s is equals to initial velocity is 0 t minus half g t square, and from here you will get. So, distance is now in this coordinate system, distance is minus of 15 meter is equals to minus half g t square. Therefore, t1 during the free fall comes out to be under root 3 second. Then the restraint phase, this is a little tricky. Here what I do first is, you remember this integral which we are solving, we were going from v1 to 0 for the maximum depth. Now, I am not going up to 0, I am going up to an arbitrary point, arbitrary x, which is of course less than 22, greater than 15, less than 22. Therefore, at that point the jumper will have a velocity v. So, with these limits I do this integration, follows the same steps, but I get v here at a certain location x. If I, so this step is purely an algebraic step which I am not discussing, I leave it to you to complete. Finally, what I have is this velocity is in this form, where z, I am making a redefinition, z is x minus 15, and if you differentiate this expression, so z dot is x dot, which is v. Therefore, my v is actually z dot. So, v is nothing but z dot. If I have this, then I can now write time elapsed. So, dz divided by this under root expression. Now, this integration I have to do. This integration requires one substitution, I mean restructuring the denominator and making a substitution, and this I again leave it to you. This is straightforward. You will get the time elapsed in this form. There is a sine inverse expression. So, you have to convert this into a complete square and do the complete the integration. Now, here this capital T is the total time of travel, and this is for the restraint phase. So, this starts after the time of the free fall has elapsed. So, root 3 was the time of free fall. So, t minus root 3 is equal to whatever is there on the right hand side, and there is a fall of z of 7. So, z remember is x minus 15. So, there is a drop of 7 meters beyond the free fall. So, from here you get t as 2.32 second. So, I will suggest that you redo this problem yourself and match with the results. Next, we are going to discuss some commonly used coordinate systems in planar curvilinear motion. The first one is Cartesian, of course, is the simplest. Then we will move to tangent normal coordinates, or what are also known as path coordinates, and then the plane polar coordinates. Subsequently, we are going to look at these. Today we are going to start with the Cartesian coordinates. Now, where do you require this? I mean, why do you need these coordinate systems? To represent, essentially to represent vectors, various vectors, acceleration, velocity, position, displacement, etc. and force. When we come to kinetics, we are going to use these coordinate systems to also represent force. But right now we are discussing kinematics, so acceleration, velocity, position, displacement. So, Cartesian coordinates are straightforward. I mean, these are discussed right from schools. So, I will make a few important points here though. When I say a Cartesian coordinates like this, I will keep this coordinate system fixed with respect to distant stars, what I have written out here. This is an important point at present, because we are going to look at what happens when this is not fixed, when this might be rotating. So, right now I am fixing this coordinate system with respect to distant stars, and that because we are discussing kinematics, I want to keep the kinematics correct. Okay. So, this defines a Cartesian coordinate frame. This I cap and j cap are unit vectors. This actually defines the frame, and we represent every vector here in terms of this I cap and j cap. So, they are unit basis vectors along x and y directions. Now, imagine a particle q moving on a path as shown here in green, and the position vector is small q. So, vectors will be represented with this half arrow on top. Unit vectors will be represented by this caret sign or a hat sign. Therefore, the representation of this q vector is qx, the component along x axis, I cap plus component along y axis times j cap. So, it is a linear combination of two vectors, one is qx I cap and the other is qy j cap. Now, how do you define velocity? Velocity is the limit when delta t tends to 0 of delta q, which is change in this vector q divided by delta t, and in the limit delta t tends to 0. Now, how do you do that? I consider a nearby point whose position vector, as I have shown here, is q plus delta q. So, delta q must be this displacement vector in this coordinate system. So, q is the displacement vector. And this is defined as q dot, and therefore, each individual components get derivated. Now, again I want to point out that I cap and j cap, which were the unit vectors, because I have fixed them with respect to the distant stars, they do not change. The reason I fixed with respect to distant stars is that they will not change, direction. They do not change magnitude, of course, they are all unit vectors, but they will not even change direction. Under only such circumstances we can say that the derivative of the frame does not exist, it is 0. Okay. So, this is an assumption that when I fix a frame with distant stars their derivatives are 0. This assumption I am making, they are negligible. So, I will say, I will consider right now that they are 0. So, if you fix with respect to distant stars, we will assume that the frames are essentially static and therefore, they do not change direction. Now, based on this I can define the instantaneous speed, which is the magnitude of the velocity vector. Magnitude of the velocity vector is the instantaneous speed. So, remember, speed is a magnitude quantity, always positive, and this is the magnitude of the velocity vector, and I have written out for you what is the expression. Next, I consider that this point is moving on this green path. You see this point, that capital Q is moving on this green path. Now, delta small q is the displacement, whereas this delta s is the distance covered as the particle moves from this location at time t to this location at time t plus delta t. So, delta s is the time along the path, please note this very carefully, delta s is the distance travelled along the path. Now, if I do that, then average speed, I define average speed as this distance travelled. Now, this can be finite distance along the path divided by delta t. Now, here there is no limit as delta t goes to 0, I mean there is no limit. So, this is finite, this can be finite distance travelled, finite divided by finite time elapsed, and that is the average speed, whereas the average velocity, please remember that velocity is a vector quantity. So, average velocity is this displacement vector, the displacement vector delta q by delta t, and this displacement vector can be a finite quantity, I mean, and delta t also can be a finite quantity. So, that is average velocity. Acceleration is defined in the limit delta t tends to 0, delta v by delta t. So, I look at the velocity vectors at 2 instants of time as shown here. One is at t plus delta t, the other velocity was at t. I have taken them, I am comparing them, taking the difference which is delta v, and then dividing it by delta t and taking the limit delta t goes to 0, and that is qx double dot. Now, the coordinates are getting differentiated 2 times, again the frame does not get differentiated. So, qx double dot I cap plus qy double dot j cap. Now, you should note this very carefully, that velocity is always tangential to the path, but there is no such restrictions on acceleration. Acceleration can be arbitrarily directed. Okay. Now, let us look at a problem. Determine the launch angle theta of a projectile with the initial velocity u for reaching a point x y. So, I am launching a projectile. Now, these projectile problems you have done before. So, I will go through this quickly. U is the launch velocity. So, this is the magnitude of the velocity vector and it is launched at an angle theta. I want to find out for what theta it will reach x y. Now, suppose I get a solution for theta, then I can reach x y of course, but if I do not get a solution, which means it is not feasible to reach, and hence that is why I ask, and hence determine the reachable region in the x y plane. So, reachable region of a projectile, this is very important calculation for artillery guns for example. Now, the coordinates of the projectile, the particle can be very easily obtained, you have seen this before I am sure. So, the x coordinate varies as u cos theta times time, and y coordinate varies as u sin theta times time minus half g t square. Now, the path of this particle can be found by eliminating this time. So, you eliminate time here, you solve for time from here, t is equals to x by u cos theta, and you substitute in here, and then you will obtain, this is the path equation, equation of the path, you will obtain the path equation. So, when you simplify the path equation, you get this expression. Now, here note that we have set out to find out theta, and theta turns out to be in this form. So, cos 2 theta, sin 2 theta, etc. Rest of it is given as x y. Okay. The way to solve this such an equation, so this is of the form a cos 2 theta plus b sin 2 theta is equals to c. Now, to solve such equations, we make these kinds of substitution. Cos 2 theta is 1 minus z square by 1 plus z square, and sin 2 theta is 2z by 1 plus z square, where z is tan theta. These are standard substitutions which you know. And if you do the substitution, you come to this quadratic equation in z. Remember, we are finding out theta, and theta sits in z, z is tan theta. So, we have to find out z. Okay. Then this quadratic equation has a solution of this type. You know how to solve a quadratic equation. Now, here is the discriminant delta. Now, depending on the value of delta, you will have solutions, as you know. If delta is greater than 0, there are two real solutions, as I have shown you here. You can reach that x y by two paths, that means launching at two angles. But if delta is less than 0, then the quantity under the square root sign is negative, and therefore, you have a complex solution. A complex solution means you cannot find a real theta. That means a solution does not exist, which means such a point x y, see the discriminant is a function of u, x, y and g. Therefore, depending on where you want to reach, what is your initial launch speed, what is the acceleration due to gravity, so that will decide the sign of this delta. So, you cannot reach arbitrary points. So, when delta is less than 0, it is beyond the reach of the launching system. Therefore, when delta is exactly equal to 0, then you have two repeated solutions. You have two repeated solutions, and this point therefore lies on the boundary of reachable and the unreachable space. So, on the inside you have the reachable space, on beyond that you have the unreachable space. So, what is this boundary? So, the boundary is when delta is equal to 0. Boundary is when delta is equal to 0, that is the boundary, because less than 0 you are unable to reach, greater than 0 you have two ways of reaching. Therefore, equal to 0 is where you can find, that is the last point that you can reach. And if you see this equal to 0 expression, this is a quadratic expression. So, if you write y as a function of x, this is a quadratic in x, and this is that, and this quadratic, as you can see here, the sign is negative. Therefore, it is concave downwards. This is called the envelope of reach. This curve defines the envelope of reach of the projectile, and this is a parabola, of course. So, let me summarize. We have discussed motion in one dimension, and we have looked at Cartesian coordinate system. We are going to continue this with more coordinate systems. We will discuss coordinate systems like tangent normal and polar coordinates. So, I will conclude the lecture here.